as it is a collision, unlikely that energy will be conserved. But very likely that momentum will be conserved. So, what has momentum just before the collision? What's that? All right, so the ball has momentum just before the collision. After the collision, what things are moving? The ball and the rod. So they are both moving. They must both have momentum. So if we assume that this is the before side and this is the after side, before the collision, just the ball has momentum. Does it have linear momentum? Sure, it's going in a straight line, has linear momentum. Anything that's moving has linear momentum. The question always is, does it have angular momentum? And that requires reference, relevance. So does it have angular momentum relevant to the problem? Yes. Yeah, because there's angular momentum with respect to the rod. So we kind of speed up its motion and talk about what happens just before the collision. And in this case, it has the angular momentum of a point mass, r perpendicular, mv. Unless, of course, you're David. And David decided to treat it as a point mass with an angular speed. Now, he's not wrong. Instantaneously, at the moment of contact, we can treat it as a point mass that has an angular speed. I'd be careful doing this if I were you, because there are definitely circumstances where this will not work. But it happened to work here, and it worked because of a certain set of conditions that were true. But let's take a look at what those conditions are. If we treat it as a point mass that has an standard angular momentum, then its moment of inertia would be m because it's a point mass, and its velocity, we'd say omega, but we're looking at its linear speed at the bottom, which would be v over x, where x represents this distance. We're just using v equals omega times r, but saying that the x that's here represents the x that's here. If we work this out, we'll get mxv, or in the case of this problem, x is r perpendicular mv. These things have to work out in this way. Here's the condition why this works. The ball strikes the rod at an angle that is perpendicular to the torque arm. Under any other circumstance, this wouldn't work. So keep that in mind, David. It served you in this case, and it's just fine. I would encourage you to use this whenever it's a point mass, because it will also take into conditions where we can use r mv sine of the angle. Those are conditions that do occur. Very seldom do we talk about them in this class, but they could. So if the ball had been traveling this way and struck the end of the rod, then the way in which you had done it would not have worked. All right? But kudos to you. It worked in this instant and would give the exact same answer. All right. After the collision, two things are moving. The point mass is moving, so it has angular momentum, lowercase l, it bounces back. And the rod is moving, it has angular momentum, l. A lot of you tried to combine the two like we did yesterday, but the ball didn't stick to the rod. The ball bounced back. So this will be r perpendicular mv for the ball after it bounces back, plus I omega for the rod. Let's put the pieces together here. Before the ball strikes the rod, r perpendicular is the 2 meters from the pivot point all the way down to the bottom. So 2 times its mass, 0.25, times its velocity, v, which was 3 meters per second. That is applying all the information to the angular momentum of a point mass. Any question there? This has to equal the ball bounced back. It bounced off the rod the same distance away from the pivot point, so R perpendicular is still 2. The mass of the ball, still 0.25. Bounced backwards, that's negative 1 meters per second. A bunch of you forgot the negative sign, but momentum has direction. You have to take direction into account when doing these problems. So if you made the right positive, you're going to have to make the left negative. Plus I omega, well, this is a rod, 1/3 ml squared times omega. The rod has a mass of 0.5, has a length of 2. You put all that together, and you find that omega equals 3 radians per second. Yepers. So go back all the way to the beginning of this semester when we were doing linear momentum problems. I know it's a long time ago, but bear with me. It'll help understand what happens in this next question. Consider that I have just a box. It's sliding on some frictionless surface to the right, 3 meters per second, and has a mass of, say, 2 kilograms. And another box that is currently not moving left or right, but is dropped onto the first box as it's moving. So that at some point in the future, the two boxes are moving together with some combined velocity v. Assume the red box has a mass of 1 kilogram. Could you find the final velocity of the two boxes after the collision? There's nothing special here. We've done this problem before. See if you can figure it out. Just take a quick second. So this one was easy, right? Do you remember how to do this? This would be considered a perfectly inelastic collision. It would be no different than if the box had been sitting still in front and the green box ran into it. The only difference is that it's on the top, so you have to hope that there's sufficient friction so that the top box comes to rest with respect to the bottom box before falling off. The problem still behaves the same. The only box with horizontal momentum before the collision is the green box. After the collision, both boxes have horizontal momentum, but we don't know what the combined velocity will be. Until we do a little work, doing the math, we find that the velocity is going to be 2 meters per second. Okay? Seem familiar from the way back when stuff? So here is that same problem, but as a rotational problem. Imagine I have a disc that is rotating on a frictionless platform about its center and rotating at 3 radians per second. Let's assume it has mass of 2 kilograms, huge disc, and say radius of 1/4 of a meter, and it's spinning. And I have another disc above it that is not spinning and is going to be dropped onto the first disc, like the way old record players used to do it. Except this time, there's nothing powering the disc. It's just on a friction-free surface. So that afterwards, we'll have a system in which there are 2 discs, one directly in contact and on top of the other, and both of them have some combined speed. What will be the final angular speed of the system as one disk drops onto the other? I got it to work. Yeah, I'll show you what we have to do on your iPad when we're done. It's not a big deal. All right, so there's not a lot to do here. You're going to treat this like a perfectly inelastic collision, but for something that's spinning. So we have just one disk spinning. So its angular momentum would just be whatever the moment of inertia of the disk is times its angular speed. And then after this collision, there would just be two disks spinning with some final angular speed. So we can put the values in if we want, but do you also all realize that the moment of inertia just doubles because the two disks are the same? So probably the system will have half the velocity after the collision. If you don't see that, we could run the numbers if you'd like. So before the collision, it's a disk, so 1/2 mr squared times its initial speed of 3 radians per second. This would be the this would be the angular momentum before the collision. And then after the collision, two disks. So the first disk, 1/2 times 2 times 0.25 squared plus 1/2 times 2 times 0.25 squared. This would be the moment of inertia of the system. There's two disks spinning now, but it's probably going to have a lower final speed. That's all there is here. All right? I want to show you another example that I think you need to see. Because we have limited time today, I'm trying to provide all of them. What if instead we have the same disk spinning at the same speed? So it's got a initial speed of 3 radians per second. It's still 2 kilograms is pretty big for this example, but we'll go with it. 2 kilograms, 0.25 meters. And we're going to put droplets of something sticky on the edge so they stick to the disc when they hit it. So oil or something like that. Let's say each droplet is big because this is a pretty small, this is a pretty heavy wheel. So let's say each droplet is 50 grams. So it's more like Jell-O packets all being dropped on there right at the edge. So how many Jell-O packets would it take until the disc is spinning at 2 radians per second? Now this one's a little different. For one, they're asking a different question, how many Jell-O packets? But they're telling us the final speed, that it's going to slow down from 3 radians per second to 2 radians per second. First, does everybody see what's happening here? What's happening to each droplet? Do you see that each droplet increases the moment of inertia of the object because it sticks to the edge. And therefore, each droplet is, by increasing the moment of inertia, is causing the speed to decrease. So there's a couple ways to approach this problem. Is it clear to you that the disk is still going to have a moment of inertia of 1/2 mr squared? Does that make sense to all of you? Is it also clear that each droplet is a point mass at the edge of the disk? So that means each droplet has a moment of inertia of mx squared, or 0.05 times 0.25 squared. This is the moment of inertia of each droplet. This is the moment of inertia of the disk. If there's no external torque, then the angular momentum of this system has to stay the same. So drawing a line from my before and after, before a droplet touches the disk, I'm going to have an angular momentum of 1/2 mr squared times omega, which is 3. After a droplet strikes it, the disk is still there, but I also now have 1 droplet's worth of inertia added to the disk. And that's going to lower the velocity by a small amount. Everybody see that okay? Well, do you see that every droplet just adds a little more weight to the outside edge? We're trying to figure out how many droplets it will take until the final speed is 2. Right? Each droplet slows it down a little, but we're looking for how many droplets. How much mass do we have to put on the edge in order for it to slow down to 2? Again, just a collision question asked a little different. Now again, I know the numbers, I know you like doing the number part. I just want to show you examples. Can I show you another example? Because I think this next example is one that's going to combine a few things and it might surprise you. So let's look at another example that might have a bit of a surprise in it. This represents the ground. I have a rod. So I have this rod, and I'm going to try and set this up so it looks like I want it to look. There's a ball directly below the pivot point. All right. So the rod is fixed so that it can swing about a pivot point. It's being held sideways, and it swings downwards, hits the ball, and after striking the ball, it stops and the ball takes off. So it looks something like this. Pull it sideways. Something on my desk. Guess not. Here we go. Still can't do it. There we go. So it swings down, hits something, but when it swings down, it stops moving and the object it hits takes off. This problem combines some things together. Not sure if you see all the things that are being combined together, so I wrote it in 3 steps. There's the part where the rod is at rest, but is horizontal. And then between here and here, the rod swings downwards until it strikes the ball. In striking the ball, the rod comes to rest and the ball takes off. Now, I don't think they would talk about the middle step here. I think they would only tell you about the beginning and the end, and you would have to infer the middle step. But the middle step's important because from here to here is conservation of energy. Is it clear to you that there's something that changes height? That the rod's center of mass changes height? And then is it clear that there's a collision here? This problem has 2 steps. This one's worth laying out the things you have to do. So think about the things that you have to do here. And as we are pressed for time, I didn't know we'd had club scheduled today. So in order to make sure we can get through all of the examples I want you to see, we might push this one along a little bit. Do you remember doing this kind of conservation of energy problem a couple weeks ago? It's important to recognize that it's the motion of the center of mass that determines the change in height for this problem. So when calculating the gravitational potential energy, you take a look at how the center of mass changes height. So I think we can all say that it's going to be about that. Let's go with the same rod from our first quiz today. Let's say it's 2 meters long and has the same mass, 0.5 kilograms. The hard part about these problems is knowing what thing is conserved. So again, the change in height kind of is a big indicator. That's what's going to give the object velocity, but it's also going to change its angular momentum. So although we have mgh here, we're going to have 1/2 I omega squared here. That's the conservation of energy part. But in the collision, we're going to have angular momentum for the rod just before hitting the ball, and then angular momentum for the ball just afterwards. All right.